right, let's begin Chapter 3. Section 3.2 is on nodal analysis. So sometimes you'll find that you don't have any circuit elements in parallel or series, and there's just not really any way to reduce the circuit. And when that happens, nodal analysis is a really good technique for solving for the voltages within the circuit. And there's some very simple steps to do nodal. Now you'll notice in your text that they do it a little bit differently. They think more of it in terms of currents going in, currents going out. They set things equal to each other. You'll get the same answers either way. I'm going to do it a way I think is a little bit easier to understand. So take a look at the book, compare it to the way we're doing it, and do whichever way is more comfortable for you. All right, so the first step for nodal is to pick a reference node. Typically we picked where ground is. We haven't been drawing ground in our circuits, but ground is always present. So we'll say this is our reference node. Then we want to assign a label to every node in our circuit except the reference node. So let's see how many nodes we have. We have one down here, our reference. We've got one right here, right? All these things meet here. This is all one node. Let's call that V1. Then we have one node right here. Let's go ahead and call that V2. And that's all the nodes we have. So again, you can't look at circuit elements to determine nodes. You have to look where they meet. So we have three nodes, V1, V2, and our reference node. So they're all labeled. Our second step is to apply KCL at each node. So we're going to use the fact that the sum of the entering currents equals the sum of the leaving. And then we want to solve a simultaneous set of equations. And there's different ways to do that. We'll talk about that in a minute. But here's how I like to teach nodal analysis. Very simple technique. We want to start at V1. And we're writing currents. So remember, V equals IR, Ohm's law, or I equals V over R. Okay? So what is my voltage across this? Well, it'll be V1 minus whatever's on this side, which is 0, divided by 10. That would be my current. So my current here is V1 minus 0 over 10. Now clearly I don't need to write the minus 0, but I will to remind you what we're doing. So all we're doing with that voltage is, remember, if we have VA, VB, then our voltage VAB is equal to VA minus VB. That's what we're doing here, V1 minus 0. Dividing it by 10 then gives us the current. So for this branch, I'm going to get V1 minus 0 over 5. And then I have 6 amps leaving. I'm defining all of these as leaving as I'm writing them because it's V1 minus 0. That means I'm defining my current this way. V1 minus 0. Defining my current that way. So leaving plus 6. I'm going to do it again. Define it as leaving. So plus V1 minus, now instead of 0, I have V2. Remember, this is what we're doing. VA minus VB. So V1 minus V2. I hope this fits on the screen. Divided by that resistor, 2. Set that all equal to 0. That might not be on the screen, but all we did was write equals 0. All right, so I'm going to reduce this equation down. Multiply through by 10. So multiply this whole entire thing by 10. You get V1 plus 2V1 plus 60 plus 5V1 minus 5V2 equals 0. And if I combine my like terms, I'll get 8V1 minus 5V2 equals negative 60. I'm going to put this in a box. This is my first of 2 equations that I need. All right, so at V2, let's write that one. At V2. Again, I want to define everything as leaving, because when I do that, it makes my math very easy. And I can always set everything equal to 0 instead of having to put things on both sides of the equal sign, which is the way the book does it. Again, nothing wrong with that, but I think it can be a little bit more confusing. So we're defining everything as leaving. V2 minus V1 over 2 V2 minus 0 over 4 I wanted to find my current that way, but it's actually going that way. Entering, so I need to write minus 6 and then minus 3 equals 0. Again, remember these are currents. This is V over R, current. V over R, current. This is already in terms of current, so I don't need to do anything but write down the number. Current, current. Okay, so let's reduce this down. Multiply through by 8. 4V2 minus 4V1 plus 2V2 minus 48 minus 24 equals 0. Combine my like terms. Did I do something? I don't know why I multiplied through by 8. I only needed to multiply through by 4. Okay, so let's go ahead and divide 2 out of this because that was not necessary. And I'm going to get, I'm going to write my V1 first. Minus 2V1, this is 6 divided by 2, so plus 3V2. 48 and 24, move it over there, divide by 2, 36. So that was just a little algebra error by my part. I should have just multiplied by 4. Okay, so I have 2 equations and 2 unknowns. You need to solve those. Obviously, there's different ways to solve these. You can use matrices. The book talks about using Cramer's rule. It's actually in Appendix A.1 in the back of your text. So if you cannot recall how to solve 2 equations at the same time, please look at Cramer's rule. I'm also okay with you using your calculator to solve the 2 equations at the same time. Although you should be able to do this by hand as an engineer, this is not a difficult thing to do. So if we solve these, we end up with V1 actually turning out to be 0, and V2 equals 12 volts. So there's my node voltages. So now I have everything I need to know about that circuit, right? If I wanted to know the voltage across here, and I called it Vx, well, now Vx is simply equal to V1 minus V2, or 0 minus 12, or negative 12 volts. If I wanted this current, let's call it Ix. Well, I have that current now because I have the voltage. V equals IR. I keep writing that down so you'll remember. My V here is V1 minus 0. That's the voltage across that resistor. My I is what we're looking for, and my R is 5. V1 turned out to be 0, right? So I have 0 minus 0 equals I times 5. My current turned out to be 0. That's unusual. We don't normally have that happen on a problem. So that's section 3.2. Section 3.3 is nodal analysis when we have voltage sources between the 2 nodes. So take a look at that one next.